Hi everyone, let's start with chapter 1, which is based on section 1.1 in the book of Drazen and Johnson. As I said in the introductory lecture, one of our main aims this term is to understand what makes a soliton special. And in order to do that, we would like to contrast them with ordinary waves which solve linear partial differential equations. And in particular, in this chapter, we're going to discuss two phenomena that arise generically in the context of those linear waves, namely dispersion and dissipation. So let's start first with section 1.1, which would be about dispersion. So usually, localized waves spread out as they travel. And we call this phenomenon dispersion. So we'll say that these waves disperse as they travel. So we'll give a precise definition of dispersion later today. And as we've seen in the introductory lecture, dispersion prevents localized waves from being solitons. So if we want to understand what makes solitons special, we'll need to understand the phenomenon of dispersion first. So that's what we're going to do. So we'll do that by looking at a few examples of linear wave equations. We'll look at three examples in particular of slightly increasing complexity. So the first equation that we'll look at is the so-called advection equation, which is a linear first-order partial differential equation in two variables, x and t. So we'll always use one variable x for space in one dimension, and then there will be t for time. So what is the advection equation? Is the following partial differential equation: 1 over v times ut, where I remind you subscripts denote partial derivatives, so ut is partial of u with respect to t, plus ux equal to 0. And we'll assume for now that v, the parameter, is positive. This is equation 1.1. So it's quite easy to find the general solution of this equation, which is u as a function of x and t. The equation actually tells us that this depends on x and t only through their combination x minus v times t. So this holds for any function f. And in particular, the fact that the solution only depends through the combination x minus v times t tells us that this solution describes a right-moving wave with the profile f and speed, or rather velocity, v, and fixed profile f. And so this wave is right moving because we assume that v, the velocity parameter, is positive. If v were negative, then the wave would be left moving. So if we draw a plot of u as a function of x at time t equals 0, let's assume that we have some localized profile near x equals 0. Then we will find that at a later time t larger than 0, then this profile will just have translated, and now it's centered around x equal vt. But the profile will be the same because the function f is fixed. So the solutions of this equation display no dispersion. The initial localized wave didn't spread out at all. But at the same time, nothing else happens either. So this is not particularly interesting for our purposes. The next example is the so-called wave equation. There are many wave equations, but this is the most famous one, so we'll call it the wave equation, which is also a linear partial differential equation, but now it's second order. And it takes the following form: 1 over v squared utt, second derivative of u with respect to t, minus uxx equals to 0. That's equation 1.2. And now we'll take v to be positive without loss of generality, since v only appears in the equation through v squared. And famously, the general solution of this equation was found by D'Alembert. Tells us that u as a function of x and t is actually given by the superposition of two independent solutions. One is has a profile specified by a function f, and it's a function of x minus vt. And the other one is specified by, the profile is specified by a function g, and it's a function of x plus vt. So again, this holds for any functions in g. So I should say perhaps that the way to see that the general solution of the advection equation is this right moving wave, which I've written above, and the general solution of the wave equation is D'Alembert's solution written here, is to change variables from x and t to, for instance, x minus vt and x plus vt. And then it's easy to see that the equations simplifying these new variables, and it's immediate to find this solution. So I'm sure you've seen this already, but anyway, I'll leave it to you as an exercise to derive these results. Now, since in D'Alembert's solution, the dependence on x and t is only through x minus vt or on x plus vt, what we find is that this general solution is a superposition of a right and a left moving waves. With velocities plus and minus v. So if we want to plot now what happens to an initial condition, so the initial condition will look again something like this, might be some profile like this at t equals 0. But then to find out what the solution looks like at a later time, we'll have to decompose the initial condition in terms of the left moving and the right moving waves, so these functions f and g. And here, for instance, f might be like this, sorry, g, let's say that this is g, and f would be like this, so they move to the right or to the left with the velocity plus or minus v. And so at a later time, x larger than 0, f will have moved to the right, so it will be somewhere here. And g will have moved to the left. somewhere there. So it is true that the initial condition, which was localized, now has split up into two components, but both waves move at the same speed, and the two components are just completely independent. So according to the technical definition of dispersion that we'll provide later, there's actually no dispersion. So the key point here is that all waves move at the same speed. And this will mean there is no dispersion. But at the same time, there is no interactions either. The two components separately do not disperse and do not interact at all. So from our point of view, this is also not very interesting. The third example that we'll look at is the so-called Klein-Gordon equation. Which is a linear second order PDE. And it starts similarly to the wave equation with the 1 over v squared UTT minus uxx. But in addition, it has a third term, which is linear in the field U with a coefficient which we call m squared. M is a real parameter. This equation, which we call equation 1.3, is historically important. It's the first example of a relativistic wave equation if we interpret the parameter v as the speed of light. It was written independently by Oscar Klein and Walter Gordon in 1926. Klein and Gordon hoped that this equation would describe relativistic electrons of mass m. So it turns out that that's not quite the case. You need a different equation called the Dirac equation to describe electrons. But this equation written by Klein and Gordon is actually useful to describe elementary particles without spin and with mass m, for instance, the Higgs boson. Anyway, we're not really interested in the origin of this equation. So let's just try and study the general solutions of the Klein-Gordon equation. So we'll see in a few minutes that this equation is much more interesting from our perspective. And to understand that, let's first try so-called plane wave solution. Namely, we'll assume that U depends on x and t as an oscillatory exponential e to the I kx minus omega t. Where k is a real parameter, and we'll say more about omega later. So notice here that in the exponent we have I, the imaginary unit, square root of -1. And so in particular, this plane wave is a complex value for the field U. In this course, we'll mostly be interested in real equations for real fields. In particular, we are indeed interested in real solutions of the Klein-Gordon equation. But since the Klein-Gordon equation is linear, we can always superimpose different solutions by the superposition principle. And later on, we'll construct a real solution out of linear superposition of different plane waves. But for now, let's consider just this single plane wave. So, and another comment is that the name plane wave comes from the fact that if you consider the same kind of ansatz in 3 space dimensions, so where k and x now are 3 vectors, then u is constant at fixed time t along a plane. So that's the reason for the name plane wave. So we don't really have a plane in one spatial dimension, so that would just reduce to a point, but we'll keep calling it the plane wave. Okay, so what does it mean that we try a plane wave solution? Well, we're going to substitute the ansatz 1.4 in the Klein-Gordon equation 1.3. Okay, so let's see what the terms look like. So first we have something which goes like 1 over v squared. And then we have the second derivative of the plane wave with respect to time. So when we differentiate twice with respect to time, we get minus I omega squared. So we'll get a factor of minus omega squared in front, and then we'll have the plane wave exponential. And for the second term, we differentiate twice with respect to x, and we get a factor of ik squared. So we get plus k squared exponential of I kx minus omega t. And finally, the third term is plus m squared exponential of I kx minus omega t. And the Klein-Gordon equation tells us that this must vanish. Now, since the plane wave solution, this oscillatory exponential never vanishes, this means that minus omega squared over v squared plus k squared plus m squared must vanish. And so we find that the plane wave 1.4 is a solution of the Klein-Gordon equation 1.3, provided that omega and k are related as follows. So omega must be a function of k, which is given by the solution of this algebraic equation here. So we have to take a square root, so there is a sign ambiguity, and then we have v square root of k squared plus m squared. So this determines omega in terms of k. So there is this sign ambiguity indeed, but in fact, we will only keep the plus sign. And the reason for that is that once you have a solution with the plus sign, you can get a solution with the minus sign by taking the complex conjugate of 1.4 and sending k to minus k. So we can restrict to the solution with a plus sign only. So this will be equation 1.5. Okay, so at this point, let's introduce some vocabulary that we'll use in the following. Okay, which multiplies x in the plane wave solution 1.4 is called the wave number. On the other hand, omega, which multiplies t, is called the angular frequency. Then the plane wave 1.4 is an oscillatory exponential. So it's a linear combination of sine and cosine. So it's periodic both in x and in t. And we define lambda, which is 2 pi over omega, sorry, 2 pi over k, as the wavelength of the plane wave. That's periodicity in x. So if you send x to x plus lambda, you get the same value of u. And similarly, tau, which is 2 pi over omega is called the period of the plane wave, and that's the periodicity in T. And finally, any equation like 1.5, which relates the wave number and the angular frequency, is called the dispersion relation. So formula like 1.5 relating omega and k is the dispersion relation. Another thing to notice here is that we can now rewrite 1.4, the plane wave equation, as follows. So we can rewrite e to the I kx minus omega, which is a function of k times t, as exponential of I k, so which we factor out, and then we have x minus omega of k divided by k times t. So this tells us that the wave crest which we can think of the maxima of, say, the real or imaginary part of this oscillatory exponential, move at the velocity, which is given by the coefficient of t in the combination x minus velocity times t. And so we'll call this velocity c of k. That's omega of k over k. And for the Klein-Gordon equation, we can take equation 1.5, divide by k. So we'll keep only the plus sign, but we'll divide by k. And so we get v times the square root of 1 plus m squared over k squared. And if you're careful, actually, there is also a factor, which is the sine of k. The reason is that k can be positive or negative, and the square root of k squared is absolute value of k, not k. So this velocity of wave crest is called phase velocity. So the picture here is that we have this plane wave, which is moving at velocity c of k. Now, the important point in the previous formula is that the phase velocity of plane waves, solutions of the Klein-Gordon equation, actually depends on the wave number k. So we find that plane waves with different wave numbers move at different velocities. Therefore, if we try to make a lump of a Klein-Gordon field, by superimposing plane waves, with different wave numbers. In particular, we have u, which is a function of x and t, is is going to be a linear superposition of plane waves to the I kx minus omega of k times t. And since k is a continuous parameter, the wave number is continuous, a linear superposition, rather than being a finite sum, is going to be an integral. So we'll have integral dk from minus to plus infinity with a weight f of k, which we can think of as the Fourier coefficient when t is equal to 0. So here we're superimposing complex plane waves, but remember we're interested in real solutions, so we'll be interested in having a real lump of the Klein-Gordon field, so we can achieve that by taking the real or the imaginary part. So we prefer of this superposition. This is equation 1.6. We've taken a real linear superposition of different plane wave solutions of the Klein-Gordon equation. And the point is that since plane waves with different wave numbers move at different speeds, because of this dependence on k here, then this wave will disperse. This lump will disperse. Good. So right now we have introduced one notion of velocity, the phase velocity, but in fact, as we'll appreciate better later, there are two notions of velocities for a wave. One is the phase velocity that we have defined above. And I remind you, we call the phase velocity c, which is a function of the wave number k, and that's given by the angular frequency over the wave number. This is equation 1.7. And as we said, this is the speed of wave crests, or rather the velocity of wave crests. But there is a second useful and different notion, which is called the group velocity. We'll call that CG for group, again, a function of k. And this is defined as the first derivative of the angular frequency with respect to the wave number, where again, the angular frequency depends on the wave number through the dispersion relation. I will also use a prime to denote this first derivative. That's equation 1.8. So unless omega is a linear function of k and a fine function of k, then the two notions of velocity are different. And as we'll see later in an example, the group velocity turns out to be the velocity of a lump while it disperses. Good. Next, let me make a general comment. So I said earlier that the Klein-Gordon equation is a relativistic wave equation. And it turns out that energy and information travel at the group velocity, not the phase velocity. And for a relativistic wave equation, such as, for instance, the Klein-Gordon equation, I'll say more about what a relativistic wave equation is later, but if the speed of light is called v, these relativistic wave equations will always look like 1 over v squared utt minus uxx plus a function of u equal to 0. The Klein-Gordon equation is an example of that, where the function f of u is linear in u. So for it turns out that for a relativistic wave equation, the principles of special relativity imply that energy and information cannot travel faster than the speed of light, and therefore it should be the case that the group velocity in absolute values less than or equal to v, the speed of light, for all values of the wave number k. For instance, for the Klein-Gordon equation, it's easy to calculate the phase velocity and the group velocity. We have already calculated the phase velocity, and its absolute value was equal to v, the speed of light, times the square root of 1 plus m squared over k squared. On the other hand, we can calculate also the group velocity by taking instead the first derivative of the angular frequency with respect to the wave number. So I'll let you do the math. The result, when we take the absolute values, v over the square root of 1 plus m squared over k squared. Okay, so and now if we compare the absolute value of the phase velocity and of the group velocity with the speed of light v, we see that since m and k are real numbers, m squared over k squared is positive, and so the phase velocity is always greater than or equal to the speed of light, and the group velocity is less than or equal to the speed of light. So this second inequality is what special relativity tells us that should happen, so that information should not travel faster than the speed of light. On the other hand, the phase velocity can be faster than the speed of light, and this is not a problem. Here is special relativity. Next, to appreciate better what is going on with the solutions of the Klein-Gordon equation and the role of dispersion, let's look at an example. That's section 1.2. This example is the so-called Gaussian wave packet. This is the simplest example of a localized field configuration. Which, following the previous logic, we obtained by superposition of plane waves. So in the plane wave, we had to specify the coefficient in the integral over Fourier modes, integral over k. And so in particular, we'll take the function f of k equal to e to the minus a squared over k minus k bar squared in equation 1.6. So let me remind you what equation 1.6 was. In equation 1.6, we expressed u as a real part of an integral over Fourier modes over wave numbers k. So we integrated the plane waves with the coefficient f of k. So, and now we've taken f of k to be that Gaussian that is written here. And in particular, we'll take a to be positive without loss of generality and k bar to be real. And so if we plot f of k in Fourier space or in wave numbers, if k bar is somewhere here, then f of k is a Gaussian or normal distribution centered k bar with a width wave number which goes like 1 over a. So if you double a, the coefficient, the parameter a, then the width of f of k goes down by a factor of 2. So this describes a lump of field with the average wave number k bar and spread of a wave number or width in Fourier space, which is scales like 1 over a. We're not really interested in defining precisely the width and determining numerical coefficient. The important point is that it goes like 1 over a. Okay, so then from what we saw earlier, we know that u of x and t, which is given by the real part of a complex field z of x and t, solves the Klein-Gordon equation, where z of x and t is a complex solution, which is given by the integral over wave numbers k of the function f of k, which is now exponential of minus a squared k minus k bar squared times the plane wave e to the I kx minus omega of k times t. And this is a solution of the Klein-Gordon equation, provided that the angular frequency of the plane waves is related to the wave number of the plane waves by the dispersion relation. Omega is v times the square root of k squared plus m squared. So we'll stop here for today, and next time what we'll do is to try and evaluate or estimate this integral with the aim of finding the profile of u as a function of x, so in real space, not in Fourier space. See you in person next Monday. Bye.